the 2019 Bollywood film Mission Mangal, a woman scientist played by Vidya Balan gets the idea for the gravity assist maneuver, or simply called sling theory, while observing her maid frying pooris in the kitchen. The same sling theory was a primary strategy that helped the Indian Space Research Organization, that is the ISRO, to reduce the cost of the Mangalyaan mission to Mars. In the movie, the woman scientist realizes that just as the poori puffs up and uses the heat to rise, the spacecraft could use the Earth's gravitational force and a series of small burns to gain momentum and escape Earth's gravity well, thus reducing the fuel cost of the entire mission. This poori connection in the movie is not a fact, but just an anecdote used in the movie to explain the audience in simple terms and also to depict how today Indian women have become rocket builders from just poori makers. This video is not about ISRO nor about calories in a poori, but on the scientific POV behind the making of that poori. Hi, hello, vanakkam, namaskar. Welcome to POV World from Bharat YouTube channel, World through Bharat's lens. Every time you walk into your kitchen, you are not just cooking, but you are creating a pure scientific magic without even realizing it. When your dosa turns crispy, or when your poori puffs like a balloon, or when your idli rises soft and fluffy, you are actually using physics and chemistry that even textbooks struggle to explain. Your tawa becomes a mini science lab where the Leidenfrost effect makes dosas lacey, steam pressure makes pooris inflate like planets, fermentation gases lift idlis using the ideal gas law, and a simple tadka shows how heat transforms flavors with explosive power. You may not wear a lab coat, but every dish you make in the kitchen is backed by brilliant scientific principles. And this video is here to show you the amazing science hiding in your everyday Indian cooking. Let's all uncover the magic you have been creating all along. First, let's start with a universal food from South India, our very own idli. Be it a baby who has just started his or her solid food or a super senior citizen, idli is the safest food on earth. Because of its soft, easily digestible, steamed and oil-free nature, and is gentle even on the most sensitive stomach. Now, let's look at the physics behind softy. The ideal gas law describes the behavior of ideal gases with a fundamental equation PV equal to nRT, where P stands for pressure, V for volume, N for moles of gas, R is the universal gas constant, and T stands for absolute temperature. We are not going into what this equation actually means, as this is not a high school physics class, but just think of the law to describe how different gases behave with respect to pressure, temperature, and other conditions. Simply put, when temperature increases, pressure and volume of the gas increase. Coming back to our idlis. The fermentation process in the batter creates carbon dioxide gas inside the batter. As the batter warms during steaming, temperature increases and the gas expands. Thus, volume of idlis increases and idlis rise and become spongy. And also the pressure of trapped bubbles in the carbon dioxide gas shapes the texture of the idlis. Idlis are literally a live demonstration of gas expansion under heat. Next time, make sure to trap more carbon dioxide gas in your idli batter for soft idlis. The Leidenfrost effect occurs when a liquid touches the surface much hotter than its boiling point. Say, water's boiling point is 100 degrees Celsius. What will happen when it touches a surface which is hotter than 100 degrees Celsius? The water, instead of evaporating instantly, the water forms a thin vapor layer that makes the droplet hover and dance. I'm sure you have seen this when water droplets skitter across a super hot tawa. This vapor layer prevents direct contact between the liquid and the pan for a few seconds. Now coming back to our dosa batter contains water. When we pour dosa batter on a hot tawa, the water in the batter hits the pan and forms a small steam cushion and helps to spread the batter smoothly and quickly. This first contact of the batter determines whether the dosa becomes soft or crispy. If the pan is not hot enough, there is no Leidenfrost effect taking place and the batter sticks to the surface and your dosa becomes soft and patchy. If the pan is very hot, that is when the pan is in the Leidenfrost zone, the water in the batter evaporates explosively, steam lifts and spreads the batter evenly and tiny holes form, giving lacy crisp texture to the dosa. And most importantly, no sticking of the dosa to the tawa. This is why our moms check the pan by sprinkling water. If droplets dance, the tawa is ready to go. Here, the sudden evaporation of water creates micro-steam explosions, tiny craters and also uniform pore structure. More pores equals more crispiness equals a perfect hotel-style dosa. Now it's a time for pooris. A perfect poori starts with firm, well-kneaded wheat dough. When you knead atta with water, the proteins in the atta, that is the gliadin and the glutenin, form gluten strands. These strands create an elastic, stretchy network like tiny rubber bands inside the dough. This process is important because these rubber bands must be strong enough to hold steam later. Too soft dough equals weak structure of the rubber bands. Too tight dough, the steam cannot expand. And no puffing of the poori. A good poori dough is just firm and stretchy enough to trap pressure inside it. Then comes our poori rolling. We are basically flattening it evenly so that heat and pressure spreads uniformly inside the poori. If you roll your poori too thick, the steam cannot rise evenly. Again, no puffing up of your final poori. If you roll it too thin, the batter tears and the steam escapes. Again, a flat poori. A well-rolled poori behaves like a perfectly balanced membrane ready for inflation. The moment the poori touches the properly hot oil, the transformation begins instantly. Here's what happens. The moisture trapped inside the poori turns into steam. The outer layer seals quickly due to sudden and intense heat and prevents steam from escaping. Now the steam pushes outward and the gluten network, that is our rubber band strands in the poori, stretches like a balloon, inflating the poori. This is the same principle as a pressure dome or a football filling with air. If the oil is not hot enough, water won't flash into steam instantly. That is, the poori absorbs oil and stay flat, and again no puffing. Poori equals pressure physics in action. So next time your poori comes out flat up from the oil, remember to heat up the oil a little more. The sweet rasagulla begins with curdling the milk to get chena, which is then softly kneaded to make smooth, elastic, bouncy balls. This elasticity is important because rasagulla needs to expand in hot syrup without breaking. Rasgulla balls are dropped into boiling sugar syrup where two things happen. Number one, heat expands the air inside. Just like our idli batter rises, the tiny air pockets inside the chena balls expand when heated. This makes the rasgulla grow almost double in size. Water in sugar syrup creates a pressure difference. Water flows into the rasgulla from the syrup because of the osmotic pressure. This is why rasgullas become soft, juicy and spongy. Same thing happens with our gulab jamuns too. If the syrup is too thick, osmosis fails and the rasgulla becomes dense. If it is too thin, it absorbs too much water and falls apart. Perfect syrup equals perfect sponge. Next time you eat a rasgulla, remember you are enjoying a perfectly engineered little ball of science. Now it's time for a South Indian filter coffee. The famous steel South Indian filter is basically a small physics tool. In here, hot water is poured on the coffee powder. The thick decoction collects at the bottom of the filter because hot water dissolves coffee compounds through solubility and diffusion. Higher temperature of the water means faster extraction, but too hot means bitterness. That's why boiling water is avoided in a filter coffee. Science decides the taste too. Filter coffee's signature froth comes from milk proteins. When milk is heated, proteins loosen up, they trap air and small bubbles form. When you mix decoction and milk, these bubbles rise, giving that creamy top layer. This is surface tension physics plus protein chemistry. Next time you drink a filter coffee, remember every sip of that delicious, frothy, aromatic filter coffee is a warm cup of science and tradition blended together. Which science law or process did you observe in your cooking today? Let me know in the comments.